So let's talk a little bit about electric fields. So electric fields exist. The lines, by definition, start on a positive and point towards a negative. So if you see field lines, you always know that they start on positive and they end on negative. They point towards the negative, away from the positive. If the lines are further apart, it's weaker. If the lines are closer, it's stronger. If they are parallel, it means the field is constant and it's not changing. So for example, in C and D, as you go away from these charges, the lines get further apart, so it's weaker. As you get closer to the charge, it's stronger. But in A and B, they're equally spaced, so it's a constant field strength. What happens when you have combinations of charges? Well, if you have a positive and a negative, the field lines are going to curve around and make this kind of classic this classic shape. They're going to point towards the positive, and as you go out further from them, they're going to kind of bow around. And we'll talk about why that is a little later. All right, so let's just do a couple of examples. So what's really tricky in this section is being able to understand whether you're finding the force or the electric field at a location. So let's say that I ask you what is the force on the charge in newtons at the 8 centimeter mark. So I want to know the force here in the figure below. And we're going to use Q is equal to 1 nanocoulomb. And nano is 10 to the negative 9. So let's first kind of draw a diagram. So at the 8 centimeter mark, the 2Q is going to be attracted to the positive Q. And it's going to be pretty strongly attracted because they're close. So this is going to be F due to Q1, okay? And then this is going to be also attracted to this positive Q. So, and it's further away, so I'm going to draw it a little shorter. So it's going to go like this. FQ2. So when I find FQ1 and I find FQ2, this is going to be a positive value and this is going to be a negative value, right? These are in the I direction, so this will be a positive I and this will be a negative I. And first I'm going to find the magnitude of them by using Coulomb's law. So FQ1 is going to be 8.99 e to the 9 times 2Q, negative 2Q, which is negative 2 e to the negative 9 coulombs, times 1 e to the negative 9 coulombs, divided by the distance between them squared. Well, this is 8 and this is 11, so that's 3 centimeters, or 0.03 meters squared. I'll put this in my calculator. And I'm just going to find the absolute value of all this, and I'm going to assign it a direction later using our normal directions. All right, so this is going to be 8.99 exponent 9 times 2 exponent negative 9 times 1 exponent negative 9 equals, divided by the quantity, 0.03 squared in quantity, and that's going to be 1.99 or 2.00 e to the negative 5. So FQ1, let's write it down here, FQ1 is going to be 2.00 e to the negative 5, and notice that this is putting in the positive I direction, newtons. FQ2, finding the absolute value of that, it's going to be 8.99 e to the 9 times negative 2 e to the negative 9 coulombs times 1 e to the negative 9 coulombs divided by, at 8, so this is 1, 2, 3, 4, 5.05 meters squared. .99 exponent 9 times 2 exponent negative 9 times 1 exponent negative 9 equals, divided by the quantity, 0.05 squared equals 7.19 e to the negative 6. 7.19 e to the negative 6 newtons. Notice from our diagram that we said FQ2 is pointing in the negative I direction. So the net force is going to be equal to the sum of these two numbers. 7.19 e to the negative 6, it's a negative number, plus 2 e to the 5 equals around 2.00 e to the 5i newtons. Okay. So what instead, if I asked you, is what is the electric field well, you have two formulas you can use. You can either use E equals KQ all over R squared, or you can use E equals FE all over the Q at that location. Turns out this one's the easiest one to use because you know what the net force is and you know what Q is. So E, and I'm going to go ahead and leave my negative in here, is 2.00 e to the 5 in the I direction divided by negative 2 e to the negative 9 coulombs. So this is going to give me newtons per coulomb. When I start putting this in here, right, this is negative 2, so that's going to be negative 1. And 5 divided by negative 9 is 5 minus the negative 9. So it's going 1e to the negative, to the positive 14 newtons per coulomb. So what that means is that this is its magnitude. Every coulomb is going to feel 1e to the 14 newtons of force, and it's going to be pulling it. It's going to be, the direction of the field is to the west. It's westward, to the west. So if I wanted to draw that field acting here, it would be this way, and that's because it's a negative charge, right? So that's the direction of the field, but the direction of the net force is in the opposite direction. The net force is in this direction, right? It's a positive number.